I'm sharing my screen. Yeah. So today we'll start about this integrated circuits. So what is an integrated circuit? The integrated circuit is nothing but miniaturized or interconnected components embedded in a thin substrate. That is nothing but integrated circuit. Okay. So in that you have monolithic ICs are there. Monolithic ICs is nothing but that is electronic circuit that is built on a single semiconductor base substrate. There is a single semiconductor base substrate is there that you are fabricating this your electronic circuit in the semiconductor base, that is monolithic integrated circuits. In this you have two types are there: analog ICs and digital ICs. Analog ICs are nothing but this will handle the continuous signals such as audio signals. Okay, digital ICs means this will handle the discrete signals such as binary values. There are some mixed signal ICs are there. Mixed signal ICs means we are talking about AMS. AMS is nothing but analog and mixed signal ICs. So analog and mixed signal ICs that contains analog and digital circuitry on the same chip. Example like modern 4G, 3G, 4G or 5G smartphones and wireless communications. This comes under the mixed signal ICs. Okay, and so coming to the IC density, so we come with that is density and complexity. So one is SSI. SSI is nothing but small scale integration. Small scale integration means basic logic gates are there like AND gate, OR gate, NAND gate, NOR gate. So within the IC, gates per IC are only 10, less than 10 only. That comes under the small scale integration. Okay. And coming to the large scale integration, sorry, medium scale integration, you have like flip-flops, adders, and counters. Adders are counters, multiplexers are demultiplexers. So these will be range from 10 to 100. This will be range from 10 to 100. That those are nothing but medium scale integration. Okay. Next, large scale integration. Large scale integration are nothing but you have small memory chips and programmable logic devices, PLDs. We already discussed in the digital. Those are nothing but PLDs. PLDs like uh, PLA, PAL, and CPLDs. Okay, those comes under the large scale integration. So gates per IC is from 100 to 10,000. Okay, and next you have very large scale integration. So very large scale integration means gates per IC. So like you have memory chips or CPLDs, complex programmable logic. See here PLDs means it will come only PLA, and PROMs are there. PROMs will come. Okay, and very large scale integration means basically like basically it consists of gates per ICR 10,000 to 1 lakh. Okay, this is very large scale integration. And next you have VLSI. VLSI is nothing but ultra large scale integration. Um, you're talking about 8-bit or 16-bit microprocessors. So these consist of 1 lakh to 1 lakh to 10 lakhs gates per IC. Okay. And next you have giant scale integration. So in giant scale integration, we are talking about Pentium 4 processor. So more than 10 lakhs gates per IC are available. Okay. So this is the basic mainly the IC density of integration will be divided into small scale integration, medium scale integration, large scale integration, very large scale integration, and ultra large scale integration and giant scale integration. Did you understood this? Shall I move forward? Okay. So next, role of the design and fabrication. So what is the role of design and fabrication? So designer will design. Okay, designer will design this that flow we already seen. No, so the designer will design this, and those will give the photo mask. Okay, so designer will design that the total front end and back end flow. This will they will give GDS2 file, GDS2 file to give it to the fabricator. So based on the GDS2 file, that fabricator means will fabricator will design, and they will give the layout rules to the designer. Okay, and this is the role of designer and fabricator. Or suppose requirements and layout rules, that is if it is a custom layout or analog layout, So here, what analog layout designers, they will give the requirements and layout to the circuit, and circuit will give this one. Okay. So what are the fabricator role? Fabricator role is nothing but to design the rules and layout rules. Okay, design rules and layout rules, and it will specify how small and how large some features can be, and how close two different features can be. These are the roles of fabricator. Okay. Mm. So here designer role means what? So first any design is there. So first in the front end they will write the code, and after that in the back end you are working with the transistor. How many transistors are resistors or capacitors are required, and how many what is the value of that component and how they are connected. This is total done by the designer. Okay, this is the designer role. So that means he will translate the requirement, whatever the requirement, into the circuit. That is the designer role. Okay. So this is the role of designer and fabricator. Okay. CMOS chip process, if you see, first stage, what is the first stage? Design engineer will design the number of transistors, diodes, and resistance in a circuit. Okay. He will design. Okay. Second step, electrical circuits are converted into physical layouts. Whatever the electrical circuits are there, they will be converted into physical layout, and exact location of each transistor and other devices will be known, and set a marks will be made, and that is second stage. And third stage is form a mask using various processes. Suppose millions of chips will be made. Okay. This is the main steps happening in the chip manufacturing. Okay, chip manufacturing. First they will find out the number of transistors and diodes in the circuit, and second stage is they will find out these electrical circuits into physical layout. So exact location, how they need to make the exact location of transistors or devices, and they will set the mask. Okay, third stage is the various processing steps. They will make the chip. Okay, this is chip manufacturing process. Okay, so suppose if you see the diagram also, first last class we already seen, no? So you are purifying the silicon, means pure silicon. You are getting silicon crystal. That is nothing but ingot. Silicon crystal. That is nothing but what? Ingot. After that, you need to polish it the wafer. You need to polish the wafer. Okay. After that, you need to make silicon dioxide. Okay. And next, you need to do some what we call etching. Etching means what? A selected area is there that you need to remove. Selected area you need to remove. Okay. And fifth is you need to make so this fourth is etching of chip silicon, and fifth is SiO₂. Okay, so silicon dioxide you need to make. Okay, and sixth is addition of layers on the SiO₂, SiO₂, and you need to add the dopant silicon. That means N plus and P plus regions, and you need to add the metals. That is metallization, and you will get the chip. Okay, these are the steps you are following in the chip manufacturing process. Okay. So coming to the technology, so we already discussed the CMOS technology, no? So this is planar process. Planar process means you are fabricating, that means a single, suppose enhancement N MOSFET. Okay, enhancement N MOSFET, or you are fabricating enhancement P MOSFET. Okay, or you are fabricating depletion N MOSFET. Okay, only single MOSFET is nothing but planar MOSFET, depletion P MOSFET. Okay, single thing is nothing but we call as planar process. Okay, so what is planar process? These are, so first, so you are getting ingots, no? So that means pre-treatment of silicon ingots. First method is pre-treatment of silicon ingots. Okay, and wafer cutting and cleaning and drying, that is polishing. Okay, and so here, if you see basic steps in the fabrication is wafer production, epitaxial growth, oxidation, masking and lithography, etching, diffusion, and implantation, metallization, and assembling and packaging. Okay, these are the steps you are going to use in the planar process. Okay, so if you find out here, so after this, wafer fabrication, so wafer lithography process you need to do, and edge rounding, lapping. Some edges, uneven things are there that you need to make. Okay. Logic design means physical design you are doing. That physical design you are converting into mask. Okay. and wafer etching process, wafer ion implantation, and after the testing, okay, assembling and wafer probing process, wafer deposition, okay, all these techniques are done in the planar process, okay. So planar process basic steps. What are the basic steps? First, this is a silicon SiO₂ layer. This is a SiO₂ layer. Okay, this is a substrate, silicon substrate. Okay, so formation of masking on the oxide SiO₂. So that means we need to make thick oxide in the active regions and thin oxide at the gate regions. Okay, selective removal, that is etching of SiO₂. Diffusion of dopants, need to diffuse the dopants. Okay, these are the four steps you need to follow. Okay, oxidation means what? Oxidation means silicon or silicon dioxide interface is super insulator structure. So as a barrier to diffuse the air implantation, dry wetting or wet oxidation we can do by using oxidation. Okay, so that is by using oxidation we can make this silicon dioxide. Okay, and we need to do the photolithography and etching. Okay, photolithography and etching means what? You want to like by using chemical etching or UV light. So you need to remove the selected part, that is nothing but photolithography and etching. Okay, to define the geometry, uses photoresist. Okay, whatever the uh, area or region you want, that will be covered with photoresist mask, and whatever the area you don't want, that by using UV light you can etch. Okay, so makes the wafer ready for diffusion and ion implantation. So by using diffusion and ion implantation, whatever the dopants are there. So whatever the dopants, that is N plus region, suppose if it is N plus regions, by using this diffusion or ion implantation, we can diffuse these N plus sources to source and drain. Okay, it is done at the surface, not protected by the oxide, and impurities move into whatever the impurities N plus region is there. So these impurities move into the semiconductor. Okay, so as diffusion is done at high temperature, so we can go for an implantation. So one equipment is required that we'll discuss. An implantation, the impurities are accelerated with high energy, so that impurities will be available in the semiconductor. Okay, and last method is metallization. You need to make the metals for the contacts to form the ohmic contacts and interconnects. So how the metal films are formed by using CVD and PVD, and photolithography is used in the metallization. Okay, so this is the method in the basic steps in the planar process. Okay. Hope you understood what is the planar process. Same process we are using in the CMOS also. Okay. So this is the planar process. Uh, so so coating, exposing, development, transfer, and strip. This will go in the planar process. Okay. There is a clean room technique is there. Okay. A clean room means build the chip in. So we need to build the chip in clean room environment. The air is highly filtered. Okay. In that clean room, the air should be highly filtered. Machines are designed to minimize the particle production. Okay. Wafer cleaning chemically. Okay. So these all things are we are doing in the clean room techniques. Okay. Suppose unwanted impurities, those are reacted with the silicon, no? So we can avoid by using clean room technique. Okay, this is clean room technique. And the CMOS technology we already seen. Silicon wafer is typically of 100 micrometer thick. So basically, this is the CMOS technology, means twin tube technique. This is nothing but we already seen the twin tube technique. So types of CMOS fabrications are, first is well technique. We already seen CMOS fabrication technique. One is fell technique. Okay, either P well technique or N well technique. Next is twin tube technique, and next is silicon and insulator technique. Okay, so these techniques we will discuss. Okay, we already discussed this one. Okay, and coming to this P well process. So PVL process, first, these are the process we already discussed, well technique, okay. N-well process also. First what you need to do, this is the process you need to follow. First formation of N-well, okay. First formation of N-well, and define the NMOS and PMOS active regions, okay. And field and gate oxidation, formation of pattern, polysilicon, P plus diffusion or N plus diffusion, contacts cuts, deposit, over glass cuts, bonding pads. These will be done in the NVEL CMOS process. Okay, the NVEL CMOS process. Coming to latch up. Latch up you already discussed, no? What is latch up? What is latch up? Anyone can say what is latch up? We already discussed latch up in the CMOS. So latch up is nothing but. Are you there? Hello? Am I audible? Yeah. Give response, anyone? Hello? Oh, okay. Okay. Latch up is nothing but it's a generation of low impedance path in the CMOS between the power supply rail and the ground. Okay. There is a low resistance path is available. Okay. Low resistance path is available between the CMOS when you are using N-well technique. Okay. N-well technique. There we drawn the SCR, silicon control rectifier. So this is like silicon control rectifier will be, it will be like so we already seen this is so P N. Okay, you need to divide and like this circuit. Okay, a virtual network will be available between the CMOS and between the NMOS and CMOS. Okay, the virtual short. Okay, so due to this virtual short, what happens? There is a short current or a static current flows from VDD to supply voltage. Okay, there is a virtual short circuit between the power rail and ground. Okay, power rail means VDD. Okay, so due to interaction of what parasitic PNP and NPN bipolar junction transistors, it form a silicon control rectifier with positive feedback. Okay, SCR. I told you, SCR. Okay, so excessive current will flow even in permanent damage. Okay, it can cause permanent damage also. Okay, that is nothing but CMOS latch up. Okay, CMOS latch. So spacing is reduced and substrate doping is increased. Latch up susceptibility would increase. Okay. One more prevention technique means you need to go for what twin tube process. Okay. So how to prevention technique means you need to reduce R well or R sub resistance of R well. We already discussed. You need to reduce R well and R sub resistance of well or resistance of substrate. Okay, or you need to use guard rings, or you need to use tape wells, isolation trench, epitaxial layer. Epitaxial layer means you need to go for twin tube process. Okay, so twin tube process means you need to grow with the n plus substrate. Above this you need to grow this this is a lightly doped n substrate. Okay, this is n substrate. You need to grow a n plus layer, that is nothing but highly doped n plus region that you are growing on the epitaxial layer, and two wells are created. In this you need to make what we call this n plus regions on the p well and N well P plus regions on the N well. So these are acting as substrates. These are acting as substrates. Okay. So in order to overcome that latch up, you need to go for what? Tin tube process. Okay. You need to go for tin tube process. Okay. This is about the tin tube process. And coming to this one, silicon and insulator. One second. Yeah. One second. Yeah. So we'll see about oxidation, oxide growth, etching types of etching, diffusion, and an implantation. Okay, oxidation is the process by which a layer of silicon dioxide on the surface of silicon wafer, that is oxidation. Okay, so so what the oxidation? This involves high temperature ambient O2 and H2O. Okay, and oxide properties and silicon dioxide. Okay, this is the oxidation. So basically, what are the uses of oxide layer means? So this will separates the semiconductor and metal. Okay, it will be act as a dielectric also. Okay, so that is the uses of oxide layer. Okay, so dielectric layer that separates the gate terminal and source or drain or channel. Okay, in order to separate the gate terminal to the source or drain or channel, we are using oxide layer. Okay, this is formed by thermal oxidation or thin oxide layer. Okay, so basically, we'll make thick oxide for the source and drain, and thin oxide is for the gate region. Okay, and there is a locus also, local oxide of silicon also there. Okay, what is this locus? Individual devices on the chips are electrically isolated by growing the thick oxide. okay, in between the active devices. That is nothing but so this process is nothing but what low cost. Okay, we need to develop a thick oxide on the active region. That is nothing but low cost. Okay, and there is interlevel dielectric and intermetal dielectric. All those things are there. Basically, how we are doing the oxidation means there are two methods are there: dry oxidation and wet oxidation. Dry oxidation is nothing but uh, silicon is reacted with oxygen, you are getting silicon dioxide. This is a dense oxide is formed. Okay, when you are doing dry oxidation, dense oxide is formed, and this is good quality and low diffusion, slow growth rate. Okay, so by using this, there is slow growth rate is there, and we need to keep the water out from the system. This is dry oxidation. Wet oxidation means in the presence of water, we are doing silicon and water. We reacted, so we are getting silicon dioxide plus hydrogen. Okay. Uh, Relatively porous oxide is formed. Okay. Lower quality and species diffuses faster. Okay. Diffusion faster. Still good quality compared to electrochemical oxidation. Faster growth rate is there. Okay. So in the presence of water, we are doing that is nothing but wet oxidation. Okay. So these are the comparison between dry oxidation and wet oxidation. Okay. What are the issues means sodium can diffuse fast in the oxide. Sodium can diffuse faster in the oxide. So in order to avoid this, we need to use chlorine during oxidation. So what the chlorine will do? It will trap sodium. Okay. So it will trap sodium and it will make, you know that sodium plus chloride equal to what? Sodium chloride. Sodium chloride. Okay, and it helps to create volatile components of heavy metals and uses 3% of HCl or trichloroethyl. Okay, mainly why you are using chlorine means to trap the sodium. Okay, why? Because sodium may react with oxygen, and it can may form a sodium oxide also. Okay, so that is the issues. Etching. Etching. What is etching? Selective removal of material from the wafer surface, leaving the desired pattern of film on the surface. So that means I told you selective removal is nothing but etching. Okay. So etchings are two types. One is wet etching, another one is dry etching. Okay. So the steps, if you see, steps for etching in the IC fabrication. First, this is silicon wafer and this etching of material. So etched material, it may be aluminum or polysilicon or silicon dioxide. So mainly first we are using silicon dioxide only, SiO₂, and on this you need to keep photoresist material, and after that with photoresist mask you will pass the light, UV light, will pass the light. Okay, when you pass the light, so this is covered, this area we want. Okay, so this area will be not etched. So whatever this area is there, this area will be etched, this area will be etched. Okay, after that you need to so after that what you need to do, you need to etch for this also, you need to etch for this also. Photoresist removal, you need to remove this one. Okay, so after etching, this is development. After etching like this, it will be available, and after that photoresist removal, you need to remove the photoresist material, and these oxides are formed. Okay, so these are the steps for etching of IC fabrication. So this is what dry etching, this is nothing but what? Dry etching. Okay, one second. Yeah, give response. I'm getting no. My voice is clear. Shall I move forward? Anyone?
Yes,
Hello. Hello.
yes, sir.
Okay. Okay. Yeah. Okay. Thank you. Next you see wet etching. So wet etching is nothing but how you are doing wet etching means like you are using etchants. What are the etchants? Potassium hydroxide or hydrogen fluoride or boron chloride. Okay. So whatever the substrate is there, you are like you are dipping in the these etchants. Okay, these etchants. Okay, suppose if you take hydrogen fluoride is there, you are taking hydrogen fluoride, silicon dioxide react with hydrogen fluoride, you are getting what? Hydrogen silicon fluoride plus water is there. Okay, so that means whatever the etchants are there, so whatever the selected material is there, that will be taken, means removed or etched by using chemical etching, by using dipped in the etchants. Okay, So here wet etching is nothing but etching is done by using liquid chemicals. Okay, so whatever the wafer is there, that will be immersed in the etchants. Okay, unmasked. So whatever the unmasked area is there, that will be etched by using chemical reaction. Okay, either like a photoresist layer or a hard mask like oxide or nitrate layers is used to protect these wafers. We can use the for as the masking. Okay, uh, so how much of etching time is nothing but the type of material you are using. Okay, and after etching, what you need to do means you need to rinse in the distilled water, DI water. Okay, to remove some unwanted means unwanted agents, you need to rinse this wafer in the distilled water. Okay, and this is used for material for large areas. Okay, and it is isotropic. Okay, isotropic means only one single process. Okay, no other contaminants or no other chemical process will be happened in this wet etching. Okay, this is wet etching. Dry etching is nothing but removal of solvent by using what we call absence of water, absence of solvent. Okay, removal of material in the absence of solvents. Okay, mainly we use three types of dry etching. One is plasma etching, ion beam etching, and reactive ion etching. Okay, so what are these? We'll see. Plasma etching. If you see the plasma, plasma is nothing but that is a state of matter which consists of free electrons and cations. That is nothing but for plasma only. Okay, it will look like similar to gas only. Okay, we can call this plasma as a ionized gas. Plasma is what? Ionized gas. Okay, so so plasma have high number of electrons, does not move around the orbit. Okay, so this is about plasma. Just to remember what is this plasma. Okay, plasma consists of free electrons and cations. It look like a gas only, and it is called ionized gas. Okay, so what are the advantages of plasma etching over wet etching means? It eliminates the handling of dangerous acids or solvents. Okay, so we are not using acids or solvents. Okay, we use a small amount of chemicals and anisotropic etch profile, high resolution, less undercutting, and better process control. These are the advantages of plasma etching. Just try to know about this plasma etching and etching. Okay. Doping means doping means what? Like depositing the impurities in the silicon in controlled way is nothing but doping. Okay, so doping is a process of in semiconductor physics you already studied. So adding the impurities to intrinsic semiconductor to alter the properties. Okay, normally there are trivalent elements and pentavalent elements are used to dope the silicon or germanium. Okay, when you are doping with trivalent impurities, you are getting p-type semiconductor. When you are doping it intrinsic semiconductor with pentavalent impurities. Okay, trivalent impurities are nothing but we already seen boron, aluminum, gallium, and indium. Pentavalent impurities are nothing but phosphorus, arsenic, antimony, bismuth. Okay, so these are the pentavalent impurities to get a n-type material. Okay, uh, fuel is nothing but controlled depth. So next we'll see the diffusion. Diffusion means what? Solid in solid. We'll take the diffusion in at a high temperature. Okay. Distance covered is in terms of micrometer or nanometer. Okay. Diffusion. So mechanism of diffusion, if you see, hmm, yeah, diffusion. If you take 1 second, diffusion. So basically, like diffusion, how we are doing means here, uh, so here this is the there will be horizontal pipes will be there. Okay, this is nothing but a cylindrical pipe will be there. Cylindrical pipe, you are placing the wafers. What you are placing? You are placing the p-type substrates. Okay, these are nothing but silicon wafers. Okay, p-type substrates are n-type substrates. You are flowing this whatever the dopants are there. So that means you are diffusing. Suppose if it is NMOS, you have p-type substrate, p-type substrate. On the p-type substrate, you need to diffuse the n plus regions that are nothing but source and drain. No? So how you are doing means whatever the dopants are there, you are passing through this gas, and that will be so at high temperature around 2000 degrees Celsius. So you are passing this, and that will be penetrated into the substrate. Okay, So here, when you are placing these substrates in the horizontal way, that is a better uniformity and less wafer per batch will be there. Okay, this is what wafer in horizontal. You are placing your wafer in silicon wafer in horizontal. Suppose when you place the wafer in vertically, what happens means pure uniformity is there, more wafer per batch, and have smaller chamber. Okay, this is vertically you are keeping, and whatever the n plus or p plus sources are there, that you are sending to these wafers, sending to these wafers. Okay, this is the type of diffusion. Okay, diffusion. So remember, diffusion is done in the high temperature, and an implantation is done at the low temperature. So there are some issues are there. What are the issues means increase with the temperature time, limits the space between the devices. Okay, these are some issues, flittering, okay, defects, and this is diffusion summary. And an implantation means what? So this is similar to sputtering also, but an implantation we are doing with a low temperature. Diffusion we are doing with high temperature. An implantation we are doing with the low temperature. So this is the equipment. Okay. So this is the equipment at the ion implantation. Whatever the ion sources are there, that ion sources we are passing through the through this chamber. These are the accelerating tubes, and this is the focus, and here you are keeping wafer process chamber. Okay, you are keeping the wafers. Okay, the amount of this accelerating your dopants depends on the how much amount of voltage you are applying. More amount of voltage means the ions will be gone, and this will be available in the, this will be penetrate, more penetration is there. More voltage means more penetration, less voltage means less penetration. Okay, so this equipment is required when you do the diffuse means when you do this means dopants, whatever the dopants, by using an implantation. Okay, so basically, this is done at a room temperature only, low temperature, whereas diffusion is done at the high temperature. Okay, so this is an implantation. Mm, okay, acceleration. Yeah, target chamber. Okay, these are the things and go to this. Yeah. So coming to the difference between an implantation and diffusion, an implantation. So an implantation is at a low temperature process used to change the chemical and physical properties of the material. So we will do the an implantation at low temperature, whereas the diffusion it will be done so at the high temperature only. Diffusion is the motion of impurities inside the substance. Okay, we'll diffuse the impurities, okay, inside the substance. Okay, and this is isotropic and very directional, and this is isotropic mainly include lateral diffusion. Okay, this is done at low temperature, this is done at high temperature. Okay, that I told you, no, an implantation is done at low temperature, and this one uh, diffusion is done at a high temperature. Okay, amount of dopants can be controlled. Okay, so we are applying some voltage, the ions will be accelerated with some directions. The amount of the penetration of that ions n plus dopants, the dopants can be depend on how much of voltage we are applying. So small voltage means that penetration is less, large voltages penetration is more. So that means we can control the dopants in the ion implantation, but here we can't control. Okay, so whatever, why? Because they are, we are passing the gas, no, so that is diffusion from high concentration to low concentration. So we cannot control this diffusion. Okay. Here an implantation, suppose we are missing the target means we can, it can damage some surface of target also. Okay, it can damage the surface of target also. But here this is gas only. It will not damage the surface of target. Okay. So just you are placing somewhere not exactly to the target of this accelerating of dopants. So what happens? It may miss the target, and it may damage the surface of the targets. Okay, and this is more expensive. Why? Because like you need a special equipment for the an implantation. Basically, we can done with less low temperature only, but it's more expensive in nature. Okay, and comparatively, this is less only, less expensive. Why? Because So you can do with you should have some cylindrical big cylindrical pipe. In that you are placing that whatever the wafers, silicon wafers, and you are diffusing the through do your dopants to that pipe. Okay, so expensively that is less, but here this is more. Why? Because more equipment, additional equipment is required. Okay, this is about today's session.